Hello. So we still have a couple of bits to finish off on sequences and series, but we had quite a hefty session last week, so you'll be pleased to know that this is going to be an extremely light one. So what are the bits we've got to finish off? Well, there's two main bits. So basically, and you're going to love this one, is we have to be able to say whether a sequence, so remember the sequence is the one where we've just got our ordered set of numbers. So we've got U1, U2, U3, U4. So we've got to be able to say whether a sequence is increasing or decreasing. And there's absolutely nothing magical to this. It's literally a sequence is increasing if each number is bigger than the last one. There you go. But we have to be able to write that in maths terms. So in maths terms, what we say is a sequence is increasing if un plus 1, right? So that's the term after un, is greater than un, and that's got to be true for all n in the set of natural numbers. Remember this, n is an element of the set of natural numbers. And I'm useless at that. We had a little discussion last week about most definitions of the set of natural numbers for what we need start from 1. So these are just the counting numbers starting from 1. So there you go. A sequence is increasing if each element is bigger than the last one. So a sequence is decreasing if, and it's as simple as each element is smaller than the one before. And again, we've got to have for all n in the set of natural numbers. Let's see if I can do that any better. Oh, there you go, that's a better one. So I'm sure you can see that we had our two main types of sequences, didn't we? Do you remember we had arithmetic and geometric? So let's just think of arithmetic ones here. So this is where we're adding a common difference. Sorry, you may get a bit of noise there. So let's think, if the difference, the difference we're adding each time is greater than 0, then the arithmetic sequence is going to be increasing. We're adding a positive number on every time. So this condition is going to hold, so that's going to be increasing. Okay, and similarly, if d is less than 0, so we're always adding a negative number on, so we're taking a number away, it's going to be decreasing. Okay, so arithmetic sequences are really easy to see which one of these they are. Geometric, maybe not so. So let's think about this. We've got a geometric sequence, so remember that's where we're multiplying by a number each time, and we call the number r the ratio. So let's think about this. If r is positive and is greater than 1, so we're multiplying each time by a number that's bigger than 1, well, we're going to have an increasing sequence, aren't we? Each number is going to be bigger than the last. Have we missed something here? What if we start off with, so let's say r is 2, great stuff, greater than 1. What if we start with a, so the first number, or u1, right, is minus 1. What are we going to get here? So we're going to start with minus 1. We're going to multiply it by 2. We're going to get minus 2. Multiply it by 2. Minus 4. Do we have an increasing sequence? No, we don't. So actually, geometric sequences, we could write down some rules, because we could say, well, if r is greater than 1 and a is positive, we're going to have an increasing sequence. If r is greater than 1 and a is negative, we'll have a decreasing sequence. And then we'd have to think about r being less than 1. So we'd have to think about the case, this case. Okay, so we've got r is a positive fraction. So we'd have to do each case again, depending on the starting value, is it positive or negative? And then we'd have to think about, well, what about when r is negative? What's going to happen then? Right, so this is a bit more complicated. So it's not easy. It's really simple with arithmetic ones to just write down a rule. For geometric ones, there's lots of different things we have to consider. So we're not going to bother doing that, okay? So we will scrub trying to think of a simple rule for geometric. You have to think about each one in turn. Whoa, don't know what happened there. Let me get rid of that. How do I get rid of that? I have no idea what happened there, so sorry about that. So let's scrap that. So arithmetic, easy, we've got a rule. Geometric, we need to think about each individual one. So before we have a look at this, the last term I'm going to introduce to you for sequences relates to sequences like this. So suppose we have, let's say we've got a geometric sequence, and let's start off with A being 1 and R being minus 1. Okay, what's going to happen here? We're going to start with 1 and we're going to multiply it by minus 1. We're going to multiply by minus 1. We're going to multiply by minus 1, and so on and so on. So you can see with this one, we're just repeating, we're getting a repeat of these two numbers. And so this is the type of last sequence, which is called periodic. Okay, so a periodic sequence is one where you literally just have a small set of numbers. It doesn't have to be a small set, it could be a large set, I don't know why I said that, but a set of numbers that literally the sequence consists of that block of numbers being repeated over and over and over. So this is the most obvious one. And we need to be able to describe what's called the order or period of one of these sequences. So the order or period, well, that's the number of things in this block, okay? So it's the number of elements you've got in which the sequence repeats. But again, we need to be able to write these terms in a very strict mathematical language. So let's have a look. In fact, let me pull a definition for you. So here we go. Let's make that a little bit bigger. So you can see here, I've got the definitions of the increasing ones. So we've already increasing and decreasing, we've just done that. So here's our definition to look at for a periodic sequence. So let's have a look at it. A sequence is periodic if the terms repeat in a cycle. Okay, so that's just what we've said here. We've got terms and they repeat over and over again. We cycle through the same terms. So for a periodic sequence, there is an integer k such that un plus k equals un for all n in the set of natural numbers. So this is the thing we've got here. So un plus k equals un. So let's think about this one. So this was u1, u2, u3, u4. Okay, so here we can say, well, u3 is u1, u4 is u2, okay, and so on and so on. So we can always then say that u5 is the same as u3 and u6 is the same as u4 because our cycle is a cycle of 2. We're repeating every 2. Okay, we're cycling around the same 2. So for this sequence here, we've got, what have we got? We've got un plus 2 is the same as un. Okay, so every other value is going to be the same. So here, this k here, we define this k to be the period or the order. So the value k is called the order or period of the sequence. Okay, so it's useful to get used to this sort of mathematical way of expressing things because it shows you all the elements you need in a definition. So you've always got to be really careful. We've had to state here, this is an integer. So k is an integer. It's got to be a whole number because we're talking about these numbers are all natural numbers. So our k in this has got to be an integer. And we've got to define the set of elements that n comes from. So you've always got to be careful and say where things are coming from, what they belong to. So shall we just have a little look at a couple of sequences? So let's have a look. Here we go. I'm going to go with this one. Okay. So what have we got here? Well, we're just adding one each time. So we have an arithmetic sequence. And what can we say about it? Well, from what I've given here, let's assume it carries on in the same way. Because of course, it might not. You've always got to be really careful here. So we've got this sequence, but do you know what? I could just be going to go back and repeat 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Or maybe I start counting down. I haven't defined this sequence. So I'm telling you that it carries on as you would expect here. It's an arithmetic sequence. So it's an arithmetic sequence. The difference is one, the numbers are always going to go up. So what we can say about this is it's an increasing sequence. What about this one? And so on. So what have we got here? Again, assuming it carries on as you'd expect. Well, we're multiplying by 2 each time, aren't we? So we've got a geometric sequence, and we're multiplying by 2. We started with a negative, so we can see that this sequence is going to be, it's a decreasing sequence, okay. Here's another one. Okay, is it arithmetic? No, because here we add 3 and then we take away 3. We add 3 and then we take away 3. So it's not arithmetic. It's not geometric. There's nothing we're multiplying by. Or is there? So let's double check. Are we multiplying by anything here? What would we have to multiply minus 2 by to get 1? We'd have to multiply it by minus a half. Well, 1 times minus a half is not minus 2. So this is neither arithmetic nor geometric. So all we can say about this is that we can see that it repeats. Okay, so this is a periodic sequence. And what's the order? Just like before, it's a periodic sequence and of order 2, because we're going around in a cycle of 2. Now you might be wondering, well, how would I express this sequence if I wanted to define it in terms of UNs? Well, we could. Let's just have a little think here. One way where we could think about it, excuse me, is we could define it like we've defined this periodic sequence. We'd have to define what U1 is, minus 2. We'd have to define what U2 is 1. And then we can use this definition to say UN plus 2 equals UN. So that is one way we could define this sequence. Or you might think, well, I could just say that slightly less of a nice way. This is the way you would normally see it stated. But I could say that UN equals minus 2 if n is odd, when n is odd, and UN equals 1 if n is even. Okay? I haven't expressed that this would have to be for n when n is odd and for when n is even. Okay. So there are, we do have alternative ways of expressing sequences. So that's all we can say about that. It's not increasing, decreasing, it's not arithmetic, it's not geometric, it's periodic of order 2. What about this? Right, so I'm sure you can see my rule here for what I'm doing. So I'm pretty much taking the set of counter numbers, and I'm alternating the sign. So let's again just have a little think. Is it arithmetic? No, because we're not adding the same thing each time. Is it geometric? No, we're not multiplying by the same thing each time. Is it periodic? No. Okay. Is it increasing? Well, no, because they're alternating in size. Is it decreasing? No. So we can't say anything about this, okay? We could describe it to someone, we could define it somehow, and you might like to think about how could you define it. So there you go. Come up with a way where you could define this sequence without writing all the numbers out. How could you define it? So there you go. You have a little think about that. I'm sure you can come up with a way where you could define what this sequence is. But really all we're interested in at the moment is it's neither increasing, it's not decreasing, and it's not periodic. So that's the last thing we have to learn about sequences. So I'll tell you what, let's have a look at some examples, and then I will set you some in a sheet, a worksheet for you to do, have a little go at. Here we go. So you can see that these sequences are all described in terms of a recurrence relation. Well, no. These first two are defined in terms of a recurrence relation, okay, how you get one term given the term before. And this last one is defined, we just describe how you get UN. So we haven't seen anything like that before yet. So let's just have a look. What have we got to do? State whether it's increasing, decreasing, or periodic. So if we look at part A, so obviously we've got a couple of ways we could do this. Let's have a little think. What's the first thing you think when you see this sequence? The first thing I think is, oh, I'm just adding 3 on all the time. So I would say to myself, well, it's arithmetic. You don't need all this to answer the question, but I'm thinking it's arithmetic. I know what A is. The first term is 7. The thing I'm adding on each time is 3. Okay. So this is how I would think about it. Another way to, like we said, always to get a feel for a sequence is just to start writing. When you've got something like this, start writing down the first few terms. So we've got 7 given by U1, and then U2 is U1 plus 3. So we've got 10, 13, and so on. Okay, so we've got these two ways to start thinking about the sequence, and we've been asked to state what it is. So it's increasing. Now, if you were asked in an exam, you'd probably be asked to say why. So we'd have to say it's increasing, and you'd have to say because UN plus 1 is greater than UN. Okay, and you'd have to say, you tied it off nicely, something like that. Okay, but that's increasing. So what about part B? Let's have a look at this. So we've got UN plus 1 equals UN squared, and we're given a first value, U1 equals a half. So just for practice, is this arithmetic? No, we're definitely not adding the same thing on each time. Is it geometric? Are we multiplying by the same thing each time? No, because we're squaring stuff. So let's see what's happening, okay? So we've got U1 is a half. So let's just start writing out what the terms are. So we've got a half squared, hoping you can remember how to multiply fractions easily. We've got a quarter squared, 16. 16 squared. This is one of the ones you probably should know, or at least recognise, okay? When you see something like this, you should be recognising this as, oh, this is something special about this number, and one of the special things about it is it's a square number. Just get used to when you see numbers, sort of categorising them in your head a bit. It will help when you get more complicated questions to see where you might be being led. So what have we got here? Well, we can see it's getting smaller and smaller. it's decreasing. Okay, and again, you'd have to state, in this case, that un plus 1 is less than un for all n. Now I'm just going to, I use this, I think it's a brilliant way to describe things. It's an upside down capital A, and what you read is you read that as for all. Now what's interesting, and I'll try and find out for you actually, that means for all. The question is, if you write that in an A-level exam, will all A-level examiners, markers, know that that means for all? Tell you what, I'm not sure. I might slip and do it sometimes, but I suggest for you, you get used to writing for all down, unless we find out differently. Okay, so what about part C? So here's another sequence. And I said we haven't looked at any like this. un equals sine of 90 times n degrees. Okay, so you're probably fairly confident that this is neither arithmetic nor geometric because we're describing something in a totally different way. There's a clue here, sine, okay? In fact, let's grab a sine graph. I have one handy because I'm like that. Right, so here's a sine graph. Let's pop it over here. So for those of us who are rusty in remembering our sine values, we can just look at the graph. Okay, so let's pop down the first few numbers. So we've got, I'm not going to write, I was going to write U1, we don't need to do that, do we? Right, what's the first one? Sine of 90, okay? So sine of 90, you can see from here. Do you know what? Aren't I dreadful? I pulled up a cosine graph. How did I manage to do that? That is absolutely dreadful. Let's get rid of that. Oh, how embarrassing. Oh well. We've had a reminder of what it's like. Should I draw one? Do you know what? I ought to be able to draw things here, so let's have a go. Sine starts at 0. Yeah? You've got to remember how to instantly, does she haven't embarrassed herself, not recognising that I'd pulled out a cosine graph. Here we go. So starts at 0, goes through 90, 180, 270, 360, and so on. What's this value here? Maximum of 1, minimum of -1. So this is our sine curve, y equals sine of x. Let's do that. Okay, so when n is 1, so we've got sine 90, we've got 1. Sine 180, so we've got n equals 2, sine 180 is 0. 3 times 90, 270, sine 270 is -1. And then we come back to 360, 0. Okay, and then what happens? Well then, because the sine graph is periodic, this repeats itself infinitely, going in that direction, well, going in both directions, but we're only concerned with positive values again. So we're going to start repeating ourselves, aren't we? So here, the next value will be here, so we've got 1. The next value is here, because we're going every 90, 0, and so on. So what have we got here? And then we'll have -1, 0. So what have we got here? Well, you can see it's neither increasing nor decreasing, because we're flipping between 1 zeros and -1s, but it is periodic, okay? And it's periodic, here you go. The period this time is period 4, order 4. So it's periodic and the order is 4. And the reason it's periodic is because we know from the graph that sine 360 plus x equals sine of x. It repeats on 360. I'm just wondering whether, if you were asked to define this, so what we want to say is we want to be able to say, so un plus 4, we've said it's periodic of order 4, equals, let's look at the definition, it's sine 90. So let's put n plus 4 in here, n plus 4 in here. So that equals sine of 90 times n plus 4 equals sine of 90n plus 360. And from the graph we know this is sine of 90n. I've missed out all my degrees here. I'll say something in a second. Sine of 90n, which is un. So there's our proof, if you like, of why un plus 4 equals un, and it's periodic of order 4. The reason they put degrees in here is because if you haven't already come across it, there is another way to measure angles, and this wouldn't work if we were measuring it in the other way. So for those who've come across it, this would not work if we were measuring these angles in radians. If you haven't come across those yet, don't worry. Okay, so that is all the terminology about sequences and series that you need to know for Edexcel A-level at least. But there's one other thing you need to be able to do with them, and we'll just have a very quick look. And that is to be able to apply them to model real-world situations. So really all we're saying is we're taking a wordy question and we're converting that into what we know about sequences and series. So here we go, a piece of A4 paper. So A4 paper is the normal sheet of paper you get out of a printing machine, and you keep folding it in half. So you're told the thickness of the A4 paper is 0.5 mil. So work out the thickness of the paper after 4 folds. Okay, so you could say, well, I can easily do that. So part A, so there'd be nothing wrong with saying it's, so after 1 fold, you've got, well, you're going to have twice the thickness, so it's going to be 0.5 times 2 millimeters, and you could work that out. After 2 folds, so this is where you've got to work out what's happening. After 2 folds, you're going to fold again, so you're going to have this, so let's actually do that, so we've got 1 millimeter there, okay. After 2 folds, you're going to have 1 times 2, which is 2, okay. After 3 folds, you're going to have the same thing again. We're going to double this, so we're doubling each time. So after 4 folds, we're going to double 4, and we've got 8. So this, you've been asked to do something 4 times, nothing wrong with that, and it's giving you a feel for what's going on. So they're going to ask us now after 20 folds. Well, we're not going to keep doing this for 20, right? That is not what we're expected to do. So let's use this to work out what's going on. Well, what we're doing, we're doubling each time. So we have the geometric series, okay? So we needed to work that out. We've got a geometric series. We've got what's our ratio that we're multiplying by each time? Well, it's 2, we're doubling. And our first value, our starting value, was 0.5, okay? So that's what we've got. Okay, so part B, after 20 folds. Okay, so what we're being asked to do here, actually, we need to be a tiny bit careful here. So after 1 fold, so are we going to say this is U1 or is this U2? So you have to decide, be careful. If we're going to start with A equals 0.5, this would be U1, okay? Which would make this one, after 1 fold, this would be U2, this would be U3, and so on, okay? So you've got to be very careful. The other way to do it is to say, well, if I want U1 to be after one fold, then you would have to change your starting value, okay? So you have to decide how you're going to define your sequence. What is the first term of your sequence? So let's go with this. If we go with this pattern, okay, so after 20 folds, so I want to find, what is it? Which element do I want to find as I've defined this here? So we'll do it this way, and then we'll look another way. Okay, so, well, the fourth fold was U5. Okay, so I want to find here you can see here I've got to go up one number, so I want to find U21. So, definition for UN for geometric. UN, if you remember, we start off with A, and then we say, well, I will have multiplied it n minus 1 times. Okay, does that make sense? Because we're starting off with our first value, and to get the second value, we'll have multiplied by one lot of r. So U2 will be A times r. So this is n minus 1. So just make sure you're getting this right in your head. So we want to find U21, which is A times r to the 20. Pop in our values. We've got a half times 2 to the 20. Okay, and if you actually work this out, you get the answer roughly of, if I can read this correctly, it's a pretty big number, 524,288. And we're measuring, so our answer would be, so that's the value of U21. We haven't put units in here. So after 20 folds, we'd say it's going to be 524,288 millimeters. Okay, so there's our answer. But let's have a little think about this. Okay, millimeters, right? I don't know about you, but I sort of can't get a feel for this. So what would it be nicer to describe it in? It would be nicer, probably, maybe meters would be good. Okay, millimeters to meters. What does milli mean? Milli means 1,000th, right? So that would be 524,288 meters. So we've got over half a kilometre here. So, C. State one reason why this might be an unrealistic model. Think what we started with, one sheet of A4 paper, and if we use this model, we can make it after 20 folds to be 524 metres thick. So your one reason here is it's impossible, right? It's impossible to fold a sheet of A4 paper that many times. Okay. So that would be fine. And if you've ever actually tried to fold a sheet of A4 paper, or even really thin tissue paper, you can't do it. Do you know what? I can't remember. You can't do it more than about 4 or 5 times, I think. So it's just absolutely impossible. But isn't it amazing? Just doubling something, how quickly you get something really big. What you might want to do, there's a famous thing about the chessboard. Okay. What you do is you start off with a chessboard and a grain of sand or a grain of salt, or say 1p. So you start off, you put, let's do that. Let's have you put 1 pence on the first square, and then what you do is you double it each time. Okay. So you go across your chessboard and then along each row, and you double each time. So each square you double it. How much will you have at the end on the last square? Okay, so on the 64th square of your chessboard, how much have you got? Okay, just these are ways people in general In real life, people who don't know much maths, they just think, oh, that'll be all right. You're not changing it much. If someone bet you to do this, lots of people would think, yeah, it's not going to be too bad. It's actually absolutely horrendous, because once you're multiplying by a factor bigger than 1, things get big very, very quickly. Okay, so I reckon that's all we need to know. So 3 new terms, increasing, decreasing, periodic. You have to be able to state the order of a periodic sequence, and you've got to be able to apply things to real world problems. So, as always, I'll give you a worksheet. So on the worksheet, there will just be some stuff for you to have a go at with those new terms today. And I'm also going to stick on 2 exam questions from past A-level exams, so you can get a feel for what they're like. I'm not going to give you the answers to those. I want you to have a real good go and see what you come up with. So I'll pop the answers in next week's. Okay, so keep smiling, enjoy the sunshine because it's sunny this week. So get out in the garden, get some sun on your faces, and yeah, keep smiling. There you go. I'm an idiot, I know, but there you go. Right, that's all for now. Bye.